Today's lecture would be about neural networks. Neural networks are a set of algorithms that learn from data. So as we saw before, they are in the family of machine learning algorithms that can learn either in supervised or unsupervised manner. So there will be the focus for the next few lectures. And over the past 10 years, they have been a very useful tool in computer vision. They have shown very good performance across a variety of vision tasks, and that's why we'll focus on the remaining lectures on neural networks. So today we will see basically the Perceptron, which is like an early attempt at a learning machine, and it's the predecessor to the Neuron, which is used in the neural network, and also how we can use neurons to form multi-layer perceptrons or multi-layer neural networks. We'll have a look at their organization, the activation functions that we use in neural networks. We'll talk about the loss functions that are used to measure their performance. And we will see how we can use gradient descent and backpropagation to train neural networks. Also, in this lecture, I would like to talk a bit about some practical considerations in training neural networks, which I think you can find useful when you deploy them in a Neuron project. So, as I said, neural networks today are used in many applications across very different domains. With regards to vision, they are used in almost all the different tasks, like, for example, in classification, we have neural networks. In detection, we have neural networks. In semantic segmentation, we have neural networks. They're even used to control robots and control them through visual input. And they're also used in generative tasks. So when we want to generate a novel image, for example, we use a neural network. As an example, you see these pictures here. They can be used to transfer the style to another image. So the way they're developing, it's making their use broader and broader in computer vision, but also in other domains. So the widespread use of neural networks in various domains has a lot of people having headlines like, for example, that these networks can now surpass the human knowledge, and they can learn many things as the human brain. But as we will see in the class, this is really not the case. Neural networks learn, the artificial neural networks learn much differently than biological networks. And they have a lot of different properties, like, for example, they are slower than the human brain, they are more compute intensive, and need many more examples to learn compared to the human brain. So as we will see in the next lectures, they are a really nice mathematical tool, but I wouldn't say they are still yet fully fledged artificial intelligence. So just keeping this in mind whenever you see something on TV or you read an article that we're way ahead of that. And incidentally, neural networks and the ideas that support them, that are behind them, have a lot of history behind them. So they have been around for 50, 60 years. So one of the first attempts at building neural networks was by Marvin Minsky, where he developed the first neural network machine, as they called it at the time. That was back in 1950s, and Incidentally, the same person that started this work, a few years later, he wrote the book, the Perceptron, where he basically showed that this algorithm that they wanted to use to mimic the human brain was not able to learn some simple examples that we'll see later also in the lecture. And this brought a lot of dismay in the community, and people gave up basically on AI and funding and research. And this was the first AI winter, so people started moving away from AI research. Then in the 80s, after some works, and notably by Geoffrey Hinton, who is a famous researcher on neural networks, and his colleagues, they popularized backpropagation, which we'll see in the class, as an algorithm to train neural networks that perform much better than other algorithms at the time. So at that time, people starting again to have some more interest in neural networks. But again, around the end of the 90s, people started using different algorithms like random forests and support vector machines. And again, a few years ago, about 20 years ago, people started looking at neural networks again. And that was mainly because they showed a very good performance on very large scale computer vision and recognition tasks. So that brought a lot of attention to neural networks again in their new iteration that is called deep learning. And from there, basically everyone up to today, many major companies like Google and Facebook, they use machine learning and neural networks to perform very different tasks like face recognition or recognizing different events on YouTube videos, basically. So you can see that they have come a really long way from simple machines into very complex machines, as we will see in the class. But if you go back to the era of Marvin Minsky, it's interesting to see the headlines at the time. So basically, this is an article from 19. The research developed machines that were able to learn like humans, and that human knowledge is achieved by a machine, and they were able to learn by doing. And this was 60 years ago. As we know today, this is not the case. Still, even though we saw before that, we still see some similar headlines. And the algorithm in question in this article was the Perceptron, which is a predecessor to the modern neural network. So the Perceptron was introduced in 1958 by Frank Rosenblatt. And if you look at it, it's basically similar to a linear classifier. So it's a linear model that can categorize the input into belonging into one or the other class. It has some weights that it can learn. And then it has an activation function, which basically thresholds the input and gives an output, the class that the variable, the vector x, belongs to. So the perceptron was an early attempt at by scientists to mimic some properties of biological neurons, basically. The actual property they wanted to mimic was that if you have high voltage charge in the biological neuron, then at some point that neuron will fire to the rest of the neurons. So they did something similar with a mathematical model where if the input multiplied with the weights was high enough, then the neuron fired a different value, basically. But as we will see, the neuron and the artificial neuron are quite different things. So the biological neuron, it's much more complex, and it also has other properties rather than what I described. And it also takes into account temporal information of the signals that it receives. So the neuron is a much simplified mathematical model rather than an advanced replication of the biological neuron. And also an important fact is that the human brains have much more computational power than a typical computer brain, and are much more power efficient. So we're a long ways from having a real biological neuron replication, even though a lot of scientists try and replicate the neuron operations in silicon using different techniques and specific hardware. In any case, the perceptron, as I said at the beginning, is basically a linear classifier. So typically, it can be used to discriminate between two classes. So it tries to find the separating line that will divide the two classes. And that line is found by adjusting its weights. So the output of the perceptron can have two different forms depending on the formulation. You can either have the sign as the output function, which basically, again, in any case, it outputs one of two values. But depending on what you choose as your output function, it can either output 1 or -1 or 0 and 1. And it can be used for binary classification. So this is an overview of the training process of the perceptron. So first, we start off by having iterating over all our data points. And for every data point, we find the response of the classifier. And if that sample is mislabeled, so it has the opposite label than the one that it should, then we update that weight by basically an amount that is proportional to the value of the sample. And if you notice here, the X and A are multiplied. So we have A, which is the output of the perceptron, and Y, which is the label. If these two are negative, that means they are opposite. So we have a misclassification. And so then we can basically deduce that there is an error, and we update the parameters, the W and the P, which is the threshold. And we do this process until we reach a maximum number of iterations, or we have classified all the samples. So if we look at the process more thoroughly, step by step, first, we initialize the weights with some random value. Then we cycle through all the training samples. And for every, we get it linked. And if it's classified incorrectly, then our weight values by a fraction of the input multiplied by the difference between what we want as the output and what we get as the output by the classifier. And when we do that, basically, we don't add the whole value, but we had a fraction of it using a parameter R called the learning rate. And this is basically the update rule for the perceptron. So if we add this update process into the raw response of the classifier, we see that the classifier basically is updated by the square of the norm of the vector x of the input, basically. So again, if the labels are different, specifically if the target label is 1 and the classifier outputs -1, then the response is negative by the classifier, and we want to increase it so that in the next iterations it will become positive. If the target is -1 and our classifier outputs 1, then the response is positive, so we want to decrease it. So this relationship here is reflected in the difference between the ground truth and the output of the perceptron. So the perceptron can basically discriminate between linear samples that are linearly separable. So some data sets that actually we can draw a line and separate them. But unlike the SVM formulation, it does not have any indication into what is a good separating line or a good separating decision boundary. So we don't get any guarantees that we will find the best separating line. However, we do get a guarantee that it will converge to some solution. Now, in the case that our data are not linearly separable, the perceptron algorithm will converge to a minimum error solution, assuming, however, that the learning rate decays over time. That's the only assumption. And again, in this case, we will not get a best separation. However, it will find some solution. Interestingly, what Marvin Minsky showed in his famous book, The Perceptron, was that this particular algorithm could not solve the XOR function. So when we have a data set which is of this form, we cannot find a line that can separate this particular data set. And this motivated, and this was basically what caused a lot of people to decline interest in research in machine learning and neural networks at that time. So the main weakness of the perceptron at this point is that it cannot separate well the linear, non-linear classes. So to allow our models to be more expressive and define better discriminative functions, what we can do is add a non-linear activation function after the linear combination. So basically, now our model of a perceptron is more akin to a neuron, where we have a linear combination of the input with the vector W. We add a bias, and then we pass this value through an activation function to obtain some form of non-linearity. So an example of such a function that is commonly used in neural networks is the sigmoid function, which gets its name from the S shape of the curve, which, if you notice, goes from 0 to 1. So this allows it to be interpreted as a probability. So it has a probabilistic formulation that can be used in the different machine learning problems. So it can tell you basically the probability of belonging of a data point to be in one of the two classes, given, and if you threshold that probability with 0.5, you can deduce the class that the sample belongs to. And now what this allows us, when we add such an activation function, is to basically have a nonlinear mapping of our input to the output. And these neurons, with the form that we saw in the previous slide, are basically what we stack together to form a neural network. So neural networks are generally made up of layers of different neurons. And each layer, we have a number of neurons that receives input from the previous layer. It does, it performs the neuron operation, as we saw in the previous slide, and then it propagates its value to the neuron, to basically all the neurons at the later. So we can have more than one hidden layer, and we will see what the impact is of having multiple layers. Also notice that at this point, we only have connections going from one level to the next level, and not go back to the previous layer. So neurons that are arranged in such a way convert our input vector into some nonlinear output, and basically you can think of it as each layer applying a different nonlinear transformation to its own input. So we can think of it as a combination of a feature extractor, where the various layers transform the input, and at the end we have a layer that performs some form of classification. For example, a linear, a neuron with a linear activation function to do classification. Okay, so we arrange the weights into neurons, but we didn't specifically say that the reason why the activation functions are needed when we have multiple layers. It would seem much simpler just to have the multiple layers without using the activations. But having only the multiple layers, it's not enough to make our networks map complex functions. The reason is that, as we see here, the nested functions here. So in the inner nest, we have the first hidden layer. So we multiply our input with the weight matrix of that layer, then that output with the weight matrix of the next layer, and that output with the weight matrix of the third layer. So if we analyze this, we see that basically, if we multiply all the weights together, we get a new weight matrix, which makes the multi-layer non-linear linear neural network just a neural network with one hidden layer. So we basically fail to exploit the multiple layers when we don't have activation functions. That's another reason why we do need to have non-linearities in our neural networks. So the activation functions are basically necessary to learn a multi-layer network. They also add a degree of curvature to the decision boundaries. So we don't have lines anymore, but we can approximate curves. And as to the type of new activation functions we can use, basically, we want them to be differentiable, and we'll see later on why. Here are some activation functions that people have been using in throughout literature. So we have the sigmoid function, which has this S shape. We have the tanh function, which is quite similar to the sigmoid, but it's centered around 0 rather than 0.5. And more recently, we have a family of different activation functions, the rectifiers. So basically, we have the ReLU that only allows propagating positive values. The leaky ReLU, they max out in the exponential LU. And all these basically are of the same family with just different characteristics that we'll see in later lectures how they help in the learning process. So we want our activation functions to be able to be differentiable with respect to their input and be monotonic. So they should either be constantly increasing or decreasing. And these two, as well as some other properties, help with the learning of the network. So if we put all this together, we get a neural network. So notice that basically we have the similar nodes across the network. So they have more or less the same computation. So they have the weight, they have the bias, and some activation. So it's the same template multiplied across the whole network. And if you look at what this graphical representation does correspond to, is basically a nesting of different functions. So if we have two layers, we have this format here. And as we add the layer, basically, we increase the level of nesting. And you can see here at 5 layers, it becomes complex. So we have 5 different weight matrices that we have to learn. And it does not look easy. And we will see how we tackle this in the next slides. So the interesting thing with neural networks is that even with one hidden layer, there is a theorem appropriately named universal approximator theorem that says that a neural network with one hidden layer can closely approximate any arbitrary function f of x for any of its inputs. Just in simpler words, what this means is that a single layer having the inputs coming from the left and the outputs to the right, just a single layer, it can approximate any function that you can think of. So it seems like this is a really powerful a theorem. And this is an intuition behind what does the theorem actually tries to say. Basically is that we have two neurons here, and let's say we want to approximate this function right here. So with two neurons, we get something like this, which seems to approximate the general shape of the curve. As we add more weights, more neurons, what you see is that we start to approximate better the different characteristics of the function. And as we add more and more and more neurons, then this it becomes we're able to capture more details of this function. So if this seems an arbitrary function, this means that any task that we have and can imagine having an input-output relationship, then a neural network with one hidden layer can approximate it. But the key thing here is that we're not talking about computing exactly that function. The key word here is approximated. This means that if we have our function fx, for example, and the approximation of the network be gx, then we define the error that we want to have in the approximation. Then the theorem says that there is a network that will basically approximate that function up to the error that we desire. So this has some rather nice implications. So if you consider basically driving as a function, then this theorem says that there is a neural network with one hidden layer that can learn to drive even better than humans. So you can have as an input the environment, and as an output you can have the steering angle, for example, or any other driving function. And there is a neural network out there that can learn to drive in that way or even better. So it seems this is a really powerful and intriguing property of neural networks. However, what this does not say is that it does not say how we find that neural network. It just says that that it exists. So basically, it gives us a goal to look for, but it does not give us a way to find the network. So some people could say that it is useless, but at least gives you some hope, I would say. So a valid question is, if it really one hidden network can do all that, why do we bother with having deeper networks? The fact is that even if this theorem exists, it doesn't guarantee that we will find that function. So learning one hidden layer networks is more difficult, and in some cases, the approximation may require to have an infinite number of neurons. So it gets really complex to first of all find the architecture that can satisfy our error, and then finding an algorithm that can find the right weights. So that's one of the reasons that people have moved away from one hidden layer networks and moved into deeper networks. So in practice, deeper networks can usually represent more complex functions. with less number of neurons than their one-layer counterpart. They can express more compactly smooth functions that fit well with the properties of the data that we encounter in the real world. And the optimization tools that we have can be used with deeper networks and have been found to be really successful applied in deeper networks. And as we will see in the next lectures, deeper networks essentially capture the compositionality of the data. So the world is compositional. Everything is made up of smaller parts. And this is a property that the deep neural networks are able to capture. So the neural network at the moment, what we have introduced, we can scale it to basically either by the width of the number of neurons and the depth, so the number of layers that we can have. And this is basically a design choice that we have to find during the training, and there's no easy way of identifying it beforehand. So now that we saw the main components of a neural network, let's move on to how we can train it and how we can learn and find the parameters of the neural network, the W's and the B's. So given a training set of pairs X and Y, what we want to do is to adjust the weights of the neural network in order to make our network output the same results as the same mapping as our ground truth. So for this, we need to measure how well we're doing as we're training. So we want a way to evaluate whether or not the training goes well. And this is done through what we call the loss function, which basically tells us how well we are doing. And we use a process called stochastic gradient descent to update the weights. So we can think of as the weights as some tunable knobs that we can turn in order to make our neural network output the same mapping as is the one in the training set. So a loss function or error function or cost function, as it is rather called in different various research papers, is basically a function that tells us how well we are doing with respect to estimating the values in our training set. So we want to find the weights based on the fig path we get from the loss function. And this process is basically called the network optimization phase. And the choice of the loss function and the optimizer can play a critical role in how our network learns and how well it learns. So this is an example of a loss function. So it's given as with respect to the weights. So in this case, we have two weights, and you can see how the values of the different weights influence the value of the loss function. So in general, when we have a high loss, it means that we have a lot of error in our prediction, and the smaller the loss, the better. So by changing the weights, we basically traverse this loss function space, and our goal is to reach the lowest point of the function, which is down here. The catch, however, is that during this process of traversing the loss function, we don't want to fall into one of the other minimums. So if we fall into that, maybe we cannot escape by changing the weights. So this is basically the game we're playing when training a neural network. So overall, what we want to do is to drive our loss function down so that we improve our model accuracy, and do it as fast as possible without overfitting to the dataset. That is, without learning all the different noise that may exist in the dataset. So an appropriate loss function has to decrease as we do better, and increase as we move away from the ground truth. So in this case, the left part of the loss function means that we are far away from the optimal performance, and the right part means that we are doing better as the loss is at the lower values. And we expect that as we train the model, the loss function will start to go down and will keep on decreasing until it reaches the point where we cannot do any better. Okay, so ideally, we want our loss function to be convex. That is, to have more than one minimum. No more than one minimum, actually. But in many cases, these functions do indeed have more than one minimum. And that is one of the challenges in training neural networks. So we would ideally also want it to vary smoothly as we change the weights. So we want an easy way to change the weights, and that to in turn cause an improvement in the loss function. We'll see more regarding this in the next few slides. So basically, a convex function looks like the image on the left. So as you can see, in convex function, we can generally draw a line to between any 2 points in the function and not intersect that function at a third point. So that means that the local minimum is also a global minimum. On the other hand, when we have non-convex functions, then things get really messy, because as you see, there's a lot of hills, and maybe we can end up stuck in one of the other holes. So this is one of the challenges in training neural networks. So here we have some typical loss functions, or objective functions or scoring functions. So we have some functions that are mostly used for classification problems, where we want to put the data point into one or more classes. So that is either a binary cross-entropy loss for binary problems, or the categorical cross-entropy for multi-class problems. We also have sparse categorical cross entropies and the hinge loss for classification. So for regression, where we want to estimate a continuous value, then we have the mean squared error and the mean absolute error. So the cross entropy loss is mostly used for classification, and it basically comes out of the assumption that our network models a Bernoulli distribution. So we have the probability of belonging to one of the two classes modeled as a Bernoulli distribution. And by taking the, so one approach would be to maximize this probability. But since we want to solve this as a minimization problem, we add the negative sign in front of this. And we also take the logarithm of this probability so that it makes the computations easier later on. An extension to this is the categorical cross entropy loss, which basically is a summation of the multi-class probabilities. That is the probabilities for each of the different classes. And this sum stems from the fact that we again use logarithms rather than standard probabilities. So the loss function functions used for regression are the mean squared error, or L2 loss, as it is also called, and the mean absolute error, or L1 loss, as it is called. So the mean squared error basically takes the square of the error between the ground truth and the output of the neural network. And the L1 takes the absolute value of the difference between the prediction of the network and the ground truth label. So in general, both functions can be used in regression problems, but L2 is theoretically a bit more stable. However, the L1 loss is more robust to outliers. However, L2 is more commonly used in different problems. So having decided our loss function, then the next step is to see how we can update the values of our parameters, the W's and the B's for each neuron. So to start, we pick some random values for our parameters. And we will see later how the initialization affects the performance. So here we have the error function as written as an average over all our data samples. And it's convenient to write it in this way because it simplifies the training process. Assuming here we have n number of training samples. So the idea is that we pass through all the data samples, compute the loss, and using that, we'll see how to update our weight. So our goal is to minimize the loss function by finding the weights that do that. And from initially random weights, we want to choose how to adjust its value. And important aspect here is to consider how each change in the weight can affect the change in the loss function. And this basically is the theory of derivatives, which study the rate of change. So to estimate this, we will use the derivative of the loss function with respect to every weight to see how the change in a weight can influence the change in the loss function. So to find the weights that minimize our prediction loss, we will use the following update rule. Basically, we will subtract from the initial value of the weights the derivative, the value of the derivative of the loss function with respect to that weight times a learning rate, which influences, as we will see next, the step that we take during the update process. So intuitively, to understand how an update in the weight changes the loss function, you can see here that we have our loss function. And at this point, if the derivative is negative, it means that we are moving towards a lower loss value. So what we have to do is increase the value of W. So we want to invert the weight of the gradient. In the other case, if our gradient is positive, it means we're moving to an increased value of the loss function. So what we want to do is decrease the value of the weight. That's why we have the minus sign here. So along with this, as I said, we have to pass through the whole data set to calculate the derivative of the loss function. And that step is called an epoch. Whenever we have an update, we perform the actual update of the weights. That is called an iteration. And we will see later on how these two numbers affect and can be changed. So as I said, it's important there to consider that the change in the vector W is a portion of the gradient of that weight multiplied by some learning rate. And that learning rate actually is important to consider what is the effect on the whole convergence process of the algorithm. So since this alpha is determined, the amount of change in the W's will affect how fast we can reach a minimum solution. So if we have a small value of alpha, it means that we will take a lot of steps to reach the minimum. On the other hand, if we have a large value, then it will result in drastic changes in our parameter. That's so you will see we will oscillate between different values of the loss function, and we will have difficulty to reach the minimum. Just right learning rate would look like something in the middle, where we have small steps, then gradually these steps, because the loss function is decreasing, these steps also decrease, and so we reach our minimum swiftly, but without having too much jumping around or because of the value of the learning rate. But overall, finding the right learning rate is challenging, especially if we consider that in neural networks, the loss functions that are mapped are non-convex. That means they have a lot of local minima. So we can end up in any of the bumps here without being able to escape. The only way to escape is to increase our learning rate so that the weights change values at a larger rate, and so we can escape and move to another part of the loss function. To do that, a lot of people use adaptive learning rates and learning rate schedulers, where basically you start off with a small learning rate, and you may increase it or decrease it depending on how the loss function is increasing or decreasing. So the overall process of training a neural network with gradient descent basically involves iterating over all our data. We compute the network output and we evaluate the loss. And the idea is that through that loss, we will be able to update the parameters in order to reduce the value of the loss function. By doing that, we will see that at some point the weights will stop changing values rapidly because the loss function that we get is also getting smaller. So when we reach that point, we can stop our training. But something that we cannot address directly is how do we actually find the derivatives of the loss function with respect to the weights. So to find the derivative of the loss with respect to the weight, first we have to compute what is called the forward pass. That is, we forward the input through the network and we get the output of the network, and then we can compute the actual loss function. But once we compute it, how do we update the weights? So if you recall, a nested neural network, a multi-layer neural network, looks really challenging to try and find all the weights analytically, especially if we're talking about really deep networks. The question then is, how do we find an association between the inputs or the weights and the loss function? And the answer is we apply back propagation, which is a technique used to basically deal with such nested functions.